Welcome. In this video, we will explain how pilot wave theory, or Bohmian mechanics, handle the enigmatic quantum concept called spin. We will see the key ideas stated mathematically, and we will visualize them with simulations. A few notes before we continue. This video is part of Core 1, an initiative by Theories of Everything with Kurt Jaimungal. Also, this video is about single particle Bohmian mechanics, so strictly speaking, there should always be only a single particle visualized with its guiding wave. However, it is much easier to grasp the statistical dynamics if we plot multiple particles at the same time. The initial positions are selected at random, according to the squared modulus of the initial wave function, but they serve the same wave. Do not mistake these for many particle simulations. Links to many of the readily playable visualizations together with code will be available in the description. Before bringing in spin, let us first derive the elementary form of Bohmian mechanics. If you're familiar with it, you can skip ahead to the next timestamp. Derivation is surprisingly simple. We start with the Schrödinger equation, and we write psi in polar form with two real-valued functions, r and s. R is the modulus, or amplitude, and s is the phase of the complex wave psi. We simply plug this polar form of the wave into the Schrödinger equation and calculate the derivatives. Pause if you want to check the details. Wonder how one should come about this idea. An elementary motivation is simply the general usefulness of polar forms. A less random and much deeper motivation is related to the very origins of the Schrödinger equation, and how Schrödinger derived his famous wave equation starting from the so-called Hamilton-Jacobi equation of classical physics. But that's a topic for another video. Anyway, we arrive at two real equations, one for the real part and the other for the imaginary part. Let us take a closer look at the imaginary part. Remember that r is the wave amplitude, so r squared means the probability density. This is the conservation equation of the probability density, well known from standard quantum mechanics. The right-hand side is the divergence of what we interpret as the probability current J. The equation tells us, for example, that if the probability density on the left-hand side decreases in time, then on the right-hand side, the current out of that location must be positive. Makes sense. We see that the probability current is proportional to the gradient of the phase. Now, if there really is a particle in addition to the wave, would it not be quite natural for it to move with that current? And this is the postulate of pilot wave theory. There is a particle, and the particle's velocity is defined as this current divided by the density at its position. Why do we divide it by the density? The same reason why one would divide momentum by mass to get the velocity. Here's a visualization from an earlier video. Wave evolves according to the Schrödinger equation. The particle will surf on top of it. Next, what is the role of the probability density in Bohmian mechanics? The initial position is randomly selected with the probability density of the initial wave function. It is the statistical probability density of the particle. It is ordinary classical probability due to our ignorance. And here, multiple alternative possibilities plotted at once, revealing the Bohmian vision of the double-slit experiment. There is no collapse in pilot wave theory. The particle is there, somewhere, and the initial wave function reflects our limited knowledge about its precise position and velocity. See the previous video for more. This was a brief introduction to the basics. Most certainly you should take time to think about what these postulates entail, but hopefully you agree that the ideas were simple, suspiciously simple even, and that nothing unreasonable was proposed. By the way, what happened to the other differential equation, the real part? This connects to a fascinating story related to the Hamilton-Jacobi theory, but unfortunately we won't delve into it today. Alright, let's spin. Electrons have spin. How do we accommodate spinners or spiners into the Bohmian picture? Well, The Schrödinger equation did not contain spin to begin with, so naturally we should upgrade it to the so-called Pauli equation. The Pauli equation is like the Schrödinger equation, but it has two complex components, which is to say it is spinor valued. Since it has two components, it no longer has a single phase, so we cannot use the phase gradient to define the probability current. Let us remind ourselves of this other well-known presentation of the current density. Pause if you want to check the details of these standard calculations. We see that the current is also proportional to the imaginary part of the gradient of psi, scaled by conjugate psi. This expression readily lends itself to spinorial generalization like this. The form is the same. The multiplications are simply replaced by their natural spinorial counterparts. If you know spinors, good. But this video is focused on the concepts and visualizations. The probability density in spinorial case is the sum of the components. It is a rather natural extension. But the key idea is that, as we have obtained a more general notion of probability current, we can define the guiding law in an identical fashion as being proportional to the flow, divided again by the density. And this is how we obtain the main part of the guiding equation. Conceptually, it is the same, only in terms of more advanced mathematical objects. But there is, in fact, an entirely new element that is missing still. This is the extra term. It arises from the curl of the spin vector field. For now, let us note that it will not in any way affect the density of the wave equation. We see that the continuity equation takes the divergence of the current, and the divergence of any curl is automatically zero. So, this spin current term, whatever its rho, does not affect the density evolution. But it does change the local current field, and therefore it can strongly change Bohmian trajectories. Here is a free particle in a 3D box in an energy ground state. You see that the Bohmian particles appear stationary. That is because we have not added the spin current. Adding the spin current makes the Bohmian particles circulate. To be clear, we have not added any external electromagnetic field. It is solely the spin of the wave function that gives the particle this orbiting movement. If we switch the spin state to down, the direction of the circulation changes, as one might predict. In Bohmian mechanics, the elusive spin appears quite vividly. By the way, when we say spin current, we are referring to the divergence-free guiding flow. And when we say convection current, we are referring to the other flow, which survives the divergence and is the only flow affecting the probability density. Also, do keep in mind that there exists only one particle at a time, and we are simply plotting them simultaneously. Let us look at some other energy eigenstates and visualize the phase with colors. In an energy eigenstate, the phase changes in time, seen as changing colors, but the phase is spatially constant with each lobe. Therefore, the phase gradient and convective current vanish. That is why, before we add the spin current, the Bohmian particles appear stationary. But we know the picture is incomplete since, again, the spin current will create a stir. The particles are indeed orbiting inside each lobe. At this point, we emphasize that in Bohmian mechanics, spin is in the wave, not in an additional internal variable of the particle as in standard quantum mechanics. The particle has no internal structure, only position and velocity. Lastly, we can also apply a uniform magnetic field to make the orbits visually precess about the axis of the magnetic field. Here, magnetic field is pointing horizontally in the x direction. Is there an interpretation for the spin current? Spin current is similar in nature to bound currents resulting from non-uniform magnetization inside matter. Here's a magnetic wave passing through magnetized matter. The tiny circles of current represent magnetization. Remember how the inside of magnetized matter can classically be imagined to consist of tiny local current circuits. If the magnetization, the tiny currents, are constant in strength, there will be no global currents since the tiny currents neatly cancel each other out. But also, if the magnetization is non-uniform, then the tiny currents no longer perfectly cancel, and at large scales, internal currents might be created. Even though every charge and current is bound to its cell, they can still collectively add up to global currents, visualized here by linear flows of different color. Such bound current loops would have zero divergence, and one calculates them from the circulation vector field using the curl. And finally, here's a Schrödinger, or more like a Pauli spin wave, visualized in the same spirit. The spin field is represented by the arrows, but is not to be taken too literally. You can think of it as the 3D vector associated with the spiner's local spin direction multiplied by the local probability density. And you can imagine it as the circulation vector of the local current loops. And taking the curl of that circulation field turns it into the probability current field. The interpretation is just a tool for thinking, but it may clarify spin current's effect on the Bohmian particles. And, indeed, the effect is surprisingly visible. It makes the particle literally circulate around the center of the wave packet, or more generally drives it around the level sets of the density. Let us have another look at the particle in a box. Although the density does not change in time, there are density gradients inside each lobe. In our interpretation, those mean non-uniform circulation, which in turn implies emergence of bound currents. These currents trace the level sets of density, so they do not affect the probability density, but they do affect the particles. The existence of the spin current term can be rigorously derived by arriving at it from relativity. The relativistic Dirac theory fixes the physically natural current, and its non-relativistic limit contains precisely this spin current term. Therefore, it should be included in the Pauli current as we have done. Reference in the description. Stern-Gerlach is the ultimate demonstration and test of spin. But in pilot wave theory, the particles themselves do not even possess spin. The spin is in the wave, remember? Moreover, there is no collapse of the wave. How will this turn out? In this first setting, we have a tunnel where the free particle moves. There is no magnetic field yet, just to get a feeling of this unusually zoomed-in behavior. The wave is in an equal superposition of up and down components. It is in an X eigenstate, as shown by the rotation of the Bohmian particles. Such state is also a Z up-down superposition, as we wanted. Alright, let's add the magnetic field. For reasons of implementation, the magnetic field affects the whole length of the tunnel, and is switched on and off to create the split. This works just as well and makes it easier for us to focus on the essential dynamics. The red contours represent magnetic field lines. The separation of the beam happens gradually in the scale. Some particles end up, others down. Notably, there is a gap in the middle. The spin is discrete, either up or down. Quantized. The pattern is discrete because the wave function has two components, which respond in opposite ways to the magnetic field. The wave splits and the particles get carried along. What determines where the particle will end up? Answer: its location in the wave packet when the magnetic field hits. If the particle happens to reside in the upper part of the packet, the upwards bending wave component will dominate and guide it up. Conversely, if the particle resides in the lower portion of the packet, the down propagating wave component dominates and drags it down with it. In the middle there is competition between the packets, as we can see if we zoom in. A funny little dance is going on in the critical region as the two packets are competing for the particles. Indeed, upper and lower portions are a bit fuzzy here and depend on the details of the apparatus and the magnetic field. This magnetic field is physically realistic, creating asymmetric beam profiles, and that's how it is in real Stern-Gerlach experiments. But isn't the result supposed to be random? Well, it is random from an outsider's perspective since, remember, one does not know where in the packet the Bohmian particle lies. And as an extra twist, the spin current is continuously stirring particles round and round. There is much randomness, but it's due to our own ignorance. The resulting statistics are exactly in line with standard quantum mechanics. Let us address the issue that is called contextuality, which is sometimes held against Bohmian mechanics. What is contextuality? Take a coin. Is it heads or tails? Depends on which face you happen to look at. The same coin may be heads for me and tails for you. In this sense, the headness or tailness of a coin is contextual. And it's no problem since we understand that the headness or tailness is not really part of the coin itself, but the process of flipping it, for example. We switch to another simulation of the Stern-Gerlach experiment, stripped down of unnecessary details. We see again that each particle is guided up or down depending on its initial position. Suppose we turn the magnet and the magnetic field upside down. What do you suppose will happen? If you're used to thinking the particles are carrying the spin, this flipping of the magnet should flip the trajectory of the particles. A particle that originally would have gone up should now go down, right? Except, we observe that it does not. Even if the magnet is flipped, a particle from the upper portion of the packet still goes up. But that's okay, since particles do not carry the spin, they just surf the wave. The wave carries the spin, and they do flip with the magnet, as seen from the color codes of the spin up and spin down packet. The component that originally went up will in the inverted field go down and vice versa, but both packets have an identical effect on the particle. So whether the particle is guided up or down is still only dependent on its position as the splitting is enacted. What we measure is the final position of a particle. From that position, we infer a spin result. But, one more time, repeat after me, in Bohmian mechanics, the particle does not carry the spin. The spin is in the wave, and the inferred spin result is contextual. I remember the contextuality of Bohmian mechanics sounding very alarming when I first heard about it, but once you understand how spin is handled in pilot wave theory, it becomes much less mysterious. Alright, thanks again for watching, and I hope you have a great day or a good night.